Welcome to the Muxall Open IoT channel. I am your host, Michael Crane. What happens in a pellet grill controller when an igniter, fan motor, or auger motor goes bad and shorts out? What usually happens is it blows the fuse in the controller, which protects the electronics in the controller. Perfect, right? It works as designed. But what happens if we put a fuse in the controller that is underrated? Well, the fuse will exhibit what is called nuisance opening. Nuisance opening is the fuse randomly blows for no apparent reason, which is super annoying, believe me. So, what if we put a fuse in the controller that is overrated? Well, in that case, the electronics will be damaged before the fuse blows. When an electronic designer lays out a PCB and specs the electronics components, he or she decides what the load carrying capacity of the traces and components will be. When I designed the Muxall Pro BBQ Controller PCB, I designed it to handle 5 amps on the traces and components. As any good engineer will do, I over-designed it to carry more than 5 amps, maybe 7 to 10 amps, just to be safe. They should handle quite a bit of current. Alright, simple, right? Pop a 5 amp fuse in the holder and call it a day. And since I knew the electronics could handle an overload, and to prevent nuisance openings pissing folks off during a cook, I used a slow blow fuse. We might have to revisit that. What is happening in the Muxall Pro BBQ Controller when an igniter, fan, or auger shorts out or a motor locks up, that's bad enough to blow the fuse, it sometimes, but not all the time, but sometimes damages the connecting triac. What is a triac, you may ask? Triacs are like relays. When coupled with an optocoupler, the combo uses low voltage DC to control the high voltage AC. There are 4 triacs that the processor and the controller uses to turn on and off the igniter, auger, and fan. The 4th triac is for the optional pellet hopper vibrator. Each triac is rated for 12 amps and the controller fuse is rated for 5 amps. So you would think that there was plenty of headroom there to blow the fuse without damaging the triac. And yet, here we are. So this video will probably be broken up into 2 separate videos. The first video will be testing the fast blow fuse in the new quad Muxall Pro BBQ controller that I sent to a beta tester for testing. This is basically a knee-jerk fix to, to protect the triacs in the controller, so I don't keep getting them in the lab to be repaired. This second video will be diving into Fuseology, and yes, that's a real word. I Googled it. And Fuseology, as defined by Little Fuse Inc., is the characterization and consideration of other factors when selecting a fuse. So to start our journey down this rabbit hole, I did what most engineers do. I Googled it. And one of the results of my Google search was this post on DigiKey's tech forum titled Fuse I2T Rating, Melting Point, and Interrupt Rating. This DigiKey post is basically an abridged version of a document by Littlefuse titled Fuseology, the Design Guide, Fuse Characteristics, Terms, and Consideration Factors. Yeah, that sounds like fun, doesn't it? So this document starts out with saying, fuses are current-sensitive devices that provide reliable protection for systems, components, or circuits by melting under current overload conditions. Yep. Choosing the right fuse for your application can be an overwhelming, time-consuming process, even for seasoned electronic design engineers. Yeah, I was worried about that. It says this user-friendly Fuseology design guide makes the fuse selection process quick and easy. Really? Helping you optimize the reliability and performance of the application. So according to this design guide, it's a dumbed down version of how to really select a fuse. Perfect, right? All right, so the first couple of pages are the table of contents and some little fuse marketing swank. On the third page, we find this little nugget. Since these are only a few of the contributing parameters, application testing is strongly recommended and should be used to verify performance in the circuit/application. Testing is strongly recommended. Oh, that's pretty much how we got to this point, right? So reading on, we have a couple of definitions of ambient temperature and current rating, and then we come to re-rating. And in summary, this paragraph says, for 25 degrees C, which is about 77 degrees Fahrenheit for us here in the US, ambient temperatures, it is recommended that fuses be operated at no more than 75% of the nominal current rating established using the controlled test conditions. Fuses are essentially temperature-sensitive devices. Even small variations from the controlled test conditions can greatly affect the predicted life of a fuse when it is loaded to its nominal value. To compensate for these variables, the circuit design engineer who is designing for trouble-free long-life fuse protection in the equipment generally loads the fuse to not more than 75% of the nominal rating listed by the manufacturer, keeping in mind that overload and circuit protection must be adequately provided for. Yeah, you don't want to stick a big fuse in that, overrated fuse. It'll melt all the electronics, which we talked about earlier. Okay. Most traditional slow-bow fuse designs are lower melting temperatures and are therefore more sensitive to ambient temperature changes. I never knew that, but that does make sense. I don't know if it really applies to us, but anyway. Reading on, we get some info and history on naming fuse part numbers, dimensions, what slow-bow and fast-blow are, and fuse holders. Yeah. Okay, so now we get to interrupt rating. Okay, so and they say, also known as breaking capacity or short circuit rating. The interrupt rating is the maximum approved current that the fuse can safely interrupt at rated voltage. During a fault or short circuit condition, a fuse may receive an instantaneous overload current many times greater than its normal operating current. Safe operation requires that the fuse remain intact, in other words, not exploding, and clear the circuit. Okay, yeah, we're going to talk more about this interrupt rate later. Okay, so next in this document, they define nuisance opening, which, yeah, it's kind of self-explanatory. It means when the fuse pops open, you know, for no reason. Okay, so in this section, they point out of all the selection factors listed in the fuse selection checklist, which we are going to do today, special attention must be given to items 1, 3, and 6, namely normal operating current, ambient temperature, and pulses. So the first two, of course, make sense, but pulses caught my attention. Since we are not having a nuisance opening issue, I almost skipped the rest of this section, but I'm glad I didn't, because this is where we get introduced to the amp squared seconds I2T term that I see listed for fuses all over the place. Okay, so it goes on to say, for example, one prevalent cause of nuisance opening in conventional power supplies is the failure to adequately consider the fuse's nominal melting, I squared T rating. I squared T rating. The fuse cannot be selected solely on the basis of normal operating current and ambient temperature. In this application, the fuse's nominal melting I squared T rating, or I2T, I'm not sure which one to use, must also meet the inrush currents requirements, and I'm not going to read the rest. It is good design practice to select a fuse that the I2T of the waveform is no more than 20% of the nominal melting I2T rating of the fuse. And it says refer to the section on pulses in the fuse selection checklist. We will get there. So yeah, we'll refer back to this when we're selecting our fuse. That 20% has me scratching my head a little bit because as you'll see later, I don't know if that's possible. But anyway, let's move on. Next, they talk about resistance and temperature coefficients, then soldering recommendations, time current curve, UL fuses and voltage rating. These are interesting, but to keep this video short, we're going to skip those for now. We will probably come back to the time current curve later. However, to help us with selecting a fuse, we need to understand what nominal melting I2T, or amp squared seconds, is. Okay? So there are two ways to derive I2T. The first way is to send increasing pulses of energy to the fuse until it opens under 10 milliseconds. In other words, they just keep increasing the pulse energy until the fuse will blow within under 10 milliseconds. The second way is to blast one big energy pulse that is 10 times the fuse's rated current and measure how fast it blows. And I bet you that's a fun test. Anyway, either one you can get the I2T calculation from. Clearing or opening of the fuse is defined as the sum of melting I2T plus arcing I2T. And the graph below shows the area of each. A curious note states the nominal I2T values given in this publication pertain to the melting phase portion of the clearing or opening, which makes me wonder why they left out the arcing portion. But they did say at the beginning that parts were left out to make the selection easy. Okay, so loaded with our partial knowledge, we are ready to work on our fuse selection checklist. Normal operating current. Number 1. The current rating of a fuse is typically derated 25% for operation at 25C to avoid nuisance opening. And if you remember, 25C is around 77 degrees Fahrenheit. Okay, so the normal operating current of the Muxall Pro BBQ Controller is about 2 to 3 amps, right? Even with the igniter on. With a 5 amp fuse, we will be well below 25%, the 25% requirement. Okay, so check. Got number 1. Number 2, application voltage. The voltage rating of the fuse must be equal to or greater than the available circuit voltage. All right. So the Muxall Pro BBQ Controller is designed for use in countries with 240 volts mains power. So we need a fuse greater than or equal to 240 volts. So I selected a 250 volt rated fuse that will work with no problems in the US or other countries. All right. Ambient temperature, number 3. Since fuses are rated at 25C, which is about 77 degrees Fahrenheit, we need to consider this statement. If that same fuse were operated at a very high ambient temperature of 75 degrees C, additional derating would be necessary. So, yeah, we're not going to be anywhere near 75C, but the controller will because the controller will shut down at 150 degrees Fahrenheit, which is 65C. We can probably ignore this parameter, but we will consult the temperature re-rating curve if we can find one in the data sheet, okay? So we'll just put that down as we'll consult if it's available. All right. So number 4, overload current condition. The current level for which protection is required. Fault conditions may be specified either in terms of current, right, or in terms of both current and maximum time. The fault can be tolerated before damage occurs. The time current curve should be consulted. So the Muxall Pro BBQ Controller was designed for 5 amps. That's easy enough. But the second part, the time at some random overload voltage, is kind of making me scratch my head. But like the curve in step 3, they also say there's a time current curve that should be in the data sheet that we should be able to consult. And, oh yeah, it goes on to say the time current curve should be consulted to try to match the fuse characteristic to the circuit needs, while keeping in mind that the curves are based on average data. All right, so we're 2 for 2 now. We've got, we know the answers to the first 2, and the second 2 we have to consult the data sheet. So, all right. Checklist item number 5, maximum fault current. The interrupt rating of a fuse must meet or exceed the maximum fault current of the circuit. Yeah, that makes sense. Remember I said we'd get back to the interrupt rating? Well, here we are. This spec is the max current the fuse can handle without blowing up. So it says fuses listed in accordance with UL blah 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 are required to have an interrupt rating of 10,000 amps, 125 volts. Great, with some exception. Oh, I hope so. See standards and certification section below, which in many applications provides a safety factor far in excess, I'd say so, of the short circuit currents available. Yeah. Looking at the minimum IR, which is the interrupt rating for a dual rated fuse on table on page 9, we see that the nominal current rating of 5 amps, which falls between the 3.6 amps to the 10 amps range there, we need a minimum interrupt rating of 200 amps, okay? And we'll take a look at this later in the video, but we'll just put 200 amps down for right now as our maximum fault current. All right. Checklist item number 6, pulses. And this is the one that I'm most interested in. The general term pulses is used in this context to describe the broad category of wave shapes referred to as surge currents, startup currents, inrush currents, and transients. So, okay, so the only normal surge current or inrush current the fuse in our application will see is when a cold igniter is first energized. If you watched my video testing the Heat Founder quartz igniter, it would spike to 3.5 amps before dropping down to 2 amps or so. All igniters do this when first energized, but 3.5 amps is quite high for an igniter, and that's why I used it. So they go on to say, the startup pulse should be defined and then compared to the time current curve and I2T rating for the fuse. All right, and so now we have a checklist in a set of steps in the checklist. So here we go. Defining our pulse. Since the controller is already on when the igniter is energized, we can ignore the startup current, which is very small compared to the cold igniter current startup. Looking at the pulse energy model, I think F would be the closest match to our pulse. E would probably work too, but E looks more like a power on pulse to me. All right, so we know the magnitude of the pulse is 3.5 amps from the video. So now we need to determine the duration from that same video. Looking at the video, I believe about 80% of the surge power is over, or I'm sorry, I believe about 80% of the surge current is over in about 3 seconds. That kind of matches the trailing off edge of our pulse model. All right, so plugging our P and I values into the equation for F, I2T equals 1/2 times the product of I squared times T, we get an approximate value for our pulse I2T of 18 amps squared seconds. All right, are you still with me? Okay, so we'll put that down. Checklist item 6, step 2. Or should I just say 6.2? Maybe we'll do that. Determine the required value of nominal melting I2T by referring to the pulse cycle withstand chart. So, I'm guessing this pulse cycle withstanding capability graph here is for Little Fuse's products. But we'll go ahead and use it to get us into the ballpark. If we find one in a data sheet, we'll use it instead. So, how many times are we going to fire up an igniter in a barbecue grill? Okay, well, it's about like 7 o'clock in the morning. Got the barbecue all set up, and I need to refill the hopper. All right, let's fire this baby up. Okay, so I have the meat on the grill. Just stuck it closer to the middle right there, and yeah, you can see it's looking pretty good. Anyway, that's it. So let's assume there's a pitmaster out there that it's going to grill every day of the year, right? That would be 365 ignitions of the igniter. That would be 1 pulse per day for 1 year, which comes to 365 pulses per year. My Traeger is already 13 or 14 years old, I don't remember, and I plan on keeping it for another 13 or 14 years. So let's assume a lifetime service of the controller is about 25 years, right? If that thing lasts 25 years, everyone's going to be patting me on the back, if I'm still here. 25 times 365 gives us 9,125 lifetime pulses that this fuse will see. So I'll just go ahead and round that up to 10K to make it easier to use a graph, okay? So looking at the pulse cycle withstanding capability graph, we draw an arrow from 10K over to the green line. Then draw an arrow from that point down to the percent axis. This gives us an approximate value of 28%. Plugging that into the nominal melting formula, pulse I2T divided by 0.28, which is our 28%, gives us approximately 64 amp squared seconds for the nominal melting I2T. All right, so we'll just make a note of that. All right, so 6.3 is selecting a fuse using the data we've just derived. Before we do that, it seems a little out of order here. Let's take a quick look at the other checklist items, okay? So checklist item 7, physical size limitations, just points us to the fuse's data sheet. Item 8, agency approvals, points us to the standards and certification section of this guide. And checklist item 9, fuse features, points us to Little Fuse's website. Really nothing of interest for our mission today. All right, so checklist item 10, fuse holder rating. Fuse holder re-rating. This had an interesting suggestion that I never even really thought of. It says for 25 degrees C ambient temperatures, it is recommended that fuse holder be operated at no more than 60% of the nominal current rating established using the controlled test conditions specified by Underwriter's Laboratory. All right, and they also give a few reasons why this is, but yeah, I've never no more than 60%, so yeah, that's basically have to get, so for our 5 amp fuse, we have to get a 10 amp fuse holder, and I don't remember seeing I'm sure that did have a spec in the data sheet for the fuse holder. I never looked at it. And we're not going to get into that today. That'd probably be another video. Probably not as complicated, but yeah, you never know. Okay, so and last but not least, checklist item number 11 says we need to test our newly selected fuse. Yeah, that makes sense to me too. All right, enough with that. So dropping down to the standard and certification section, which we're not going to get into today, but there was a little bit of interesting information on how fuses are tested with some parameters, and one of them, which we kind of talked about earlier in this video, was the UL certified fuses must meet the following criteria. So current carrying capacity, the fuse shall carry 100% of its rated current. Well, it makes sense to me. Verification of temperature rise, the fuse shall carry 100% of its rated current until the temperature rise, and the measured temperature of the fuse contact cannot exceed 75 C. Okay, well that's new. I didn't really know that. Verification overload operation, 135%, 60 minutes maximum clearing, 200% maximum clearing of 2 minutes for 0 to 30 amp fuses, and 4 minutes for 31 to 60 amp fuses. So yeah, it's 135% of the fuse's rating. It needs to last 60 minutes max, right? And 200%, it shouldn't last over 2 minutes. Okay, so according to this, we can run the controller at 10 amps, and as long as the fuse blows within 2 minutes, it meets the UL certification. I don't know how well the controller is going to like that, but anyway, we'll move on. And this last one is the one that we talked about earlier. Verification of operation at rated voltage. The interrupt rating, remember that's the explosion one, must be 10,000 amps at 125 volts. And fuses might have a dual rating of 10,000 amps at 125 volts and a lower interrupt rating at 250 volts as found in the table below. Yeah, I'm just shaking my head on 10,000 amps at 125 volts. If you shot 10,000 amps at that controller, it would blow the controller clean out of the grill. But at least in this, it does drop a lot for the 250 volt rated fuses. So I'm glad we're putting 250 volt rated fuses in there, because at least it drops it down to a menial 200 amps. And yeah, if you shot 200 amps at the controller, it'd probably blow it out of the grill too. But anyway, and I had to Google this, right? If you're wondering why in the world some electrical outlet needed such protection, I Googled it. And I Googled mains power max short circuit current. And I highlighted a couple of them here in the answer. It says the short circuit current in a standard domestic mains electrical installation is a few thousand amps. All right, and it goes on, and then it says the interrupt capacity rating, the IC rating of an overcurrent device is a maximum fault current the device can interrupt without damage to itself. And it says most circuit breakers and fuses have an IC rating of 10,000 amps. Yeah, so these guys are probably talking about fuses that you screw into a house, electric panel, and circuit breakers that plug into a house electric panel. I doubt if they're thinking about something coming out of your wall socket, but I mean, it says a few thousand amperes, and I guess you could probably pulse that high. I guess, I don't know. I've never really tested it, so don't plan on it either. Anyway, so let's move on. So, okay, so let's find a fuse, right? The first thing I'm going to do is pull up DigiKey. They are by far my favorite supplier. So, okay, so I'm going to go to the circuit protection / fuse page so we can perform a parametric search for our fuse. So first, we select 5 amps for our current rating. Second, we select 250 volts for our AC rating, voltage rating, AC. Third, we select the physical dimension of our fuse, which is 5 millimeter by 20 millimeter. Then hit apply. and voila. All right, so we know we need a fuse that can handle approximately 64 amp squared seconds. So I'm going to go ahead and sort the list by I2T. Great, there are several fuses that fit our parameters. Wait a minute, the fuse I had in the controller probably fits these parameters. So let's take a look at that real quick. So here's the spec of the fuse that is currently in the controller. And let's compare it to our checklist. Okay, so number 1, 5 amps check. Number 2, 250 volts check. Number 3, nominal melting I2T greater than 64 amps squared. Check. And it actually supports 102 amp squared seconds. But we know this fuse is not protecting the triac. So 102 amp squared seconds is too high. So let's pull up the spec for the triac. Scrolling down to table 1, absolute maximum ratings, we find this, an I2 spec for fusing. Yay! I have looked at this spec a dozen times and have never paid attention to this parameter. All right, great. Now we know why the slow blow fuse I had in the controller was damaging the triac. It was exceeding the 78 amp squared seconds that is the max in the triac. So, okay. So back to our search parameters. Now we can select a range of melting I2T temperatures, parameters, I mean. So we need something that's greater than 64 amp squared seconds and less than 78 amp squared seconds. That's not too big of a range, but there are some fuses in that range. Okay, so sorting by price, the first fuse we come to that is in stock is this Eaton fuse. Okay, so we know the Eaton meets most all of our parameters. It looks like it also exceeds our number 5 maximum fault current of 200 amps, or greater than 200 amps, by about 1,300 amps. All right, so great. All right, so let's see if we can find the time current curve, aka the TCC, and the temperature re-rating curve. The first curve we find is this temperature derating curve. And just as a general guess, I'm guessing that the controller will probably be in the 125 degree Fahrenheit range. It's probably not going to go over that too much in most people's grills, and most of the time it'll be under that. So I think 125 degrees Fahrenheit or 51 degrees C is a good number to use in this curve, because I guarantee you running that controller at 125 degrees Fahrenheit all the time or above, it's not going to last very long. Electronics do not like a lot of heat. But anyway, I digress. Let's see. Okay, so graphing from 51C and over to the derating factor, we see that it's about 92% at 51C, approximately. So dividing our adjusted normal operating current of 4 amps by 92%, we get about 4.3 amps, which is still under our 5 amp fuse rating. Excellent. All right, so next we find our TCC graph. So this spec has got them both. Excellent. If you remember, the overload current can be defined by current greater than 5 amps, in our case, or current and time. So since our journey started because we needed to protect the triac, let's see what its spec has to say on the matter. The non-repetitive surge peak on-state current is 120 amps for 20 milliseconds at 50 hertz and 126 amps for 16.7 milliseconds at 60 hertz. Okay, you got all that? So looking at the TCC, our little fuse will be wide open before the current even gets to 100 amps. So I think we're okay. That fuse will work just fine. If you remember way back at the beginning of this video, it was talking about where it is good design practice to select a fuse such that the I2T of the waveform is no more than 20% of the nominal melting I2T rating of the fuse. If you remember, the waveform I2T was 18 amp squared seconds, and our fuse rating is about 71 amp squared seconds. And if you divide those two, you get about 25%. Yeah, we're not at the 20%, but I'm going to say that's good enough. So, ladies and gentlemen, I believe we have a winner. I'll go ahead and order these fuses up and send them out to the customers, and hopefully they'll work out just fine. So anyway, if you like this video, give it a big thumbs up. If you have any questions or comments, leave them in the comments of the video, and I'll try to answer them the best I can. Thanks for watching, and I'll see you next time. Don't forget, you can support the Muxall Open IoT channel by donation using a credit card and PayPal, or by purchasing products at the Muxall store. Details and links are in the description under this video. Well, that's it for this video. If you liked the video, give it a big thumbs up, that helps, and hit the subscribe button, that really helps. If you have any questions or comments, post them in the comments under this video. Thanks for watching, and I'll see you next time.